Hey everyone, welcome back. Sorry I haven't been posting recently. I'm a student as well, so I also have lots of stuff to do. But I'm trying to be consistent with these videos. I'm trying to post every Friday to cover the week's topics. So today we're going to start equilibrium, and we're going to use a value or another constant k, but it's going to be a capital K, not a lowercase k like in kinetics. But before we get into any problems, we have to establish some major concepts that you need to understand in order to master this material. So if anyone remembers, or from when we talked about kinetics, we didn't introduce um, equilibrium just because it was just not the right time, I guess is what I'm trying to say. So let me get rid of these lines. Perfect. Okay. So if you recall, we did a diagram with maybe concentration of something here. Like I think we'll just use concentration, and then we use time here. And remember, we had some reactant and then some product. Well, in this case, equilibrium has to do with the state in which the rate of the forward reaction is equal to the rate of the reverse reaction. So that means the reaction doesn't stop. There's no net change in the concentration. But again, that doesn't mean the concentrations are equal. It just says that they stop changing. So if we have a product, we're going to start with high concentration, and it's going to go dip down like this. This is what's going to happen to our reactant. And for our products, we're going to start with 0, and then we're going to start forming them. And then they're going to reach the static state, which is this kind of, it curves up, and then you get to this steep or horizontal line. So that's what happens with equilibrium, and that's what we're trying to analyze. Again, the concentrations aren't equal at this point. There's just no net change in them. So we're going to use this equilibrium constant called K, capital K, equilibrium. Equilibrium constant is the ratio of the forward reaction and the reverse reaction. So if you want to write it as you write it as, so K is always going to be written as K equals concentration of your products raised to their stoichiometric ratio, I'm going to name it N, and concentration of the reactants raised to the power N. So if, for example, we have an equation like Br2 gas plus Cl2 gas, and again, the double arrow means we're in equilibrium. And then we have 2Br2Cl gas, right? So the way you write the K value is concentration of your product. So we only have one product, so it's going to be concentration of BrCl raised to the second power, right? Because we need those stoichiometry ratio. This is where you can use the stoichiometry for K for equilibrium. And then we're going to do our reactants. So it doesn't matter which order it goes. You can do Br2. There's no power associated with Br2. So it's just going to be, we're not going to put anything on this, just assume to be 1. Same thing with Cl2. Cool. And notice how this problem only has gases. So your only equilibrium applies to gases, aqueous solutions, and liquids. Oh, not liquids, sorry. Just gases, aqueous solutions. But no solids. So if you have a solid, that doesn't go part of the equilibrium, and also liquid. So not this, gases and aqueous solutions are only involved in equilibrium. So that's how you write the the K equilibrium value. So I'm just going to erase this. Like I said, you don't use solids or liquids. Cool. So K is an indication of the extent of the forward reaction. So if you have something like K is greater to the 10 to the second power, that means the reaction favors forming products, right? I should zoom in. Likes forming products. It favors forming products. If you have something that K is less than 10 to the second, that means it likes to form the reactants better. It likes to do the reverse reaction. It can do both, but it favors the reactant side. And when K is equal to 1, it's equal sharing, so it doesn't matter. Right? Cool. Again, we're only going to see concentrations for K or pressure values, which we'll see in some problems. So let's do a quick example of doing K. So example 1, let's say we have H2 gas plus iodine gas goes to always an equilibrium with 2HI gas. So let's check everything is gas or liquid or aqueous, so that's good. So we can do our K equals products over reactants raised to their stoichiometric ratios. So we're gonna write this as, let's do products, we'll do HI raised to the second because it has a 2 coefficient. And we'll do H2 gas at the bottom, raised to the first, I2 gas raised to the first. So that's how you write your K equation. But let's say I give you concentrations for all of them, so you can put your concentrations for all of them. So HI has a concentration of, let me write this different. HI has a concentration of, let's say, 1.29 molar. And then we'll say that the other two, we'll say that H2 has 0.106, or sorry, I should have wrote this. H2 has a concentration of 0.106 molar, and then we'll do concentration of I2, which is equal to 0.035 molar. So yeah, your concentrations, you can plug these values into the equation. HI equals 1.29 squared molar over H2, which is 0.106 molar, times 0.035 molar. So if you plug this into your equation, you get K. You can also label it as K because we're going to have different types of Ks. But Kc, or just K, is equal to 449. So obviously this is obviously a large value for K. So that means that this reaction likes to form products or favors the products here. So when calculating our equilibrium constant, we must use our equilibrium concentrations always. So now let's talk about another important thing is the reaction quotient. Sometimes you're dealing with the reaction quotient Q. Sometimes you're dealing with a reaction that you know it's equilibrium state, but you don't know if your physical reaction or the reaction you're actually working with is an equilibrium. So Q is just like K, but again, we don't know if it's an equilibrium. It's for an arbitrary reaction or it's at a state. So it's again the same thing. Products over reactants. So concentration used in calculating Q are not in equilibrium, most likely, maybe. We're trying to figure out where it is in the reaction space. So if Q is it's less than your K, that means we have to go to the right. So we need to go towards the products or to the right of the reaction. If Q is way bigger than K, that means we have to go back. So we have to go to the reactants because we made too much product. So to the left. And if Q is equal to K, that means the reaction is at equilibrium. Right? That's not how you spell equilibrium. Equilibrium. Cool. So, and we're trying to reach K. The whole goal is to get to K, or like K, actual K value. So if we have this reaction going and we calculate that Q, or our Q is really large and it doesn't match our K, it's way above K, that means we have to go to the reactants. And if we have a Q that's really small and doesn't look like K, then we have to go to the right and make more products. And if we have a Q that's equal exactly to K, that means we're right at equilibrium and there's no change that needs to be made. Let's do a practice problem with that. So let's say they're giving us a Kc of 51. So this is our concentration for a reaction. It looks like it's going to be like the same reaction we did above. So we'll write out the reaction one more time. So H2 plus I2 gas is in equilibrium with 2IHI gas. Cool. They give us your K value. So let's do the same thing that we were given. Let's use different concentrations. So let's say I give you the concentrations. We're going to write it out. So it's going to be HI. It's going to be our Q, right? Because they already gave us, we already know our K. We're looking for a reaction quotient. Where is our reaction right now? So we're going to square that H2, I2, and then you're going to plug in the values. Let's say I have 1.0 times 10 to the negative 2 molar squared. And then we'll do 5.0 times 10 to the negative 3. These are all given. There's nothing I'm not using that is not given. So these concentration values are given. Cool. We'll plug this into our calculator. Remember, don't forget the squared. And we get a Q of approximately 1.3. So what does that mean? So if we're comparing our Q versus K, which was what? 51. So our Q is less than our K. Is it 50? Yeah, it's 51. So our Q is less than K. So what does that mean? Well, in this one, that means that we need to go to the right? Because Kc is 51. This is when it's at equilibrium. So our Q is not there yet. It needs to go make more products. It needs to favor the product. So for this reaction, must proceed to the right. Again, our Q is not the same as K. Our Q is this arbitrary state in the reaction that we're looking at that already has technically a K value, and we're trying to get it to equal K. But sometimes it's not there. That's why we use this Q value to figure out where we are in the reaction itself. So in my next video, we're actually going to do some more calculations, more examples of manipulation of K, and we're probably going to do ice tables, which is the most difficult topic in this unit.